Why does that length tension curve end? Blaine, what do you think, bud? You're pretty quiet. Blaine, what do you think? I think Blaine maybe logged in and then walked away from his computer. That's okay. Celia, what do you think?
Is it because there's always some kind of tension in your muscle?
Not bad, not bad. It's not so much that there's always some tension. It's the fact that once you get there, you're butted up against the end. Like you literally cannot go any shorter. Your contractile units are as tightly compressed as they possibly can. So you're not gonna be able to, once again, really, I mean, you're still producing that amount of force, but it literally it doesn't go any further actively. Now, why is it that we hit that peak tension and then it stops on the other end of the spectrum, guys? So we hit that peak tension, we stop over here. Why do you think that would be?
Is that the furthest that it can go without snapping?
Yes, Cam, that's the furthest you can go without tearing it off. Once you go past that one, you've literally gone through the full range and the muscle is literally snapped right off the bone. Or the tendon, the muscular junction that tears right there. One of my friends, he's a faculty member over in the forensic science department. And for a brief period of time, I played with him on the men's rugby team up in Lexington. And he got tackled in kind of a weird lateral lunge position. And a guy came down on his hips and it caused the muscle of his groin and then his, what would have been the semitendinous and semimembranous to have one of them a pretty thorough tear of the muscle off of the bone because it pushed his leg beyond what his mobility would allow. And yeah, I mean, the muscle didn't want that to happen, but physics is a harsh mistress and it just happens. Questions there, guys? So the next component to keep in mind is what's known as Henneman's size principle, which is as we're, once again, recruiting those slow twitch muscle fibers, we're going to find that the force is going to keep increasing as we're recruiting more and more individual motor neurons until finally we're tapping into those bigger, more powerful type 2 fibers, which is going to allow us to produce the greatest amount of force. So notice in this example, and this is from Henneman's size principle, you see how we start off with those slow twitch fibers and then we slowly work our way into those bigger, more powerful type 2 fibers. This is recruitment threshold, aka high, meaning we don't want to just tap into them for no reason because they require a lot of energy to use. And the body is incredibly lazy. It's trying to do the least amount of work to get you through every moment of your day, and it doesn't want to have to expend any more iota of energy than it needs. So you have to have the reason to tap in. Now, notice how it also tells you the RMs where you're going to be tapping into these fibers. So the idea is you're not really using your biggest and most powerful fibers when you're only doing in the 6 or working in the 6 to 10 rep range. And then in the 1 to 5, you're going to tap everything in. Think of it along the lines of the fiber you're tapping into with your first rep. So once you're going for any set with a weight that you can not do more than 5 reps, from the very first rep you're doing, you're pretty much tapping into every single muscle fiber you can. However, if you are to pick up a submaximal weight and try to move that as quickly as possible, that's where you're going to be producing you're going to be recruiting pretty much all of those muscle fibers. And that's where things like doing plyometrics, doing jumping, doing bounding, doing sprinting, doing throwing are going to help us do a better job of utilizing our musculature because, yeah, the load's not that heavy, but you're trying to hit that ball or throw that ball or jump as hard and as quickly as possible. And that's what's going to allow you to tap in all those fibers. Now, if you just walk in and just doing slow curls while you think about your feelings, yeah, it turns out you're only going to be tapping into these slow twitch fibers initially until they eventually fatigue out. Then you're going to tap into the bigger, more powerful fibers. And as those fatigue out, you're going to tap into what's left. So if you really push yourself to failure, meaning you're lifting that weight as many times as you can, you're eventually going to use all of your muscle fibers. If you cause yourself to lift maximally, so you're lifting the heaviest load you can, you're going to be using all of those muscle fibers. And then if you try to move as quickly as possible, you're going to be tapping into all of those muscle fibers. And when I say as quickly as possible, I'm referring to on the concentric, so on the lifting phase. On the eccentric, you typically want to be a bit more controlled if the exercise allows for it. But on the concentric, if you're constantly thinking about standing up as fast as possible from your squat, you're going to be tapping into those bigger, more powerful fibers. So they're still getting a training effect, at least metabolically. Does that make sense when we're referring to Henneman's size principle and how we'd apply that with an athlete? Thank you, guys. So what's determining our muscle fiber type is usually heavily based upon the motor neuron and how frequently that motor neuron is going to send those signals. So what we're going to find is literally the motor neurons towards our slow twitch fibers are different than our fast twitch fibers. They're going to be sending at faster rates. And when it comes to just conduction through the body for the fast twitch, however, they're going to be sending more frequent information when you're looking at things like your slow twitch fibers. Now, when I say we're looking at this, effectively these signals, and notice this is calcium and how that's going to be released in those individual cells, you have to keep in mind whenever we contract our muscles, we get what's known as an action potential, which you guys have hopefully learned about in anatomy and physiology. And that literally is an electrical signal that's going from your neurons all the way down until they finally reach the neuromuscular junction to get that muscle to contract at the end of the dendrite, or the axonal terminal, sorry. Now, this literally is where we're going to see a changing in polarity, where it's going to go from positive to negative. And using machines, what's known as electromyography, which we were going to hopefully have a lab where you guys are going to get to come in and do that, but it turns out we're no longer in person. Don't worry, I'm going to do that all by myself in the next couple days and put that up there for you guys to see. But what you can literally do is look at this electrical activity going to the muscle, and then how that's going to correspond to how much force we're producing or the power we're trying to produce from that muscle. Now, what's really cool, and some of my friends do this type of research, is they utilize systems that are incredibly complex, that are measuring all of the muscular activity from the electricity that's coming off of it, which is known as raw electromyography signals. Now, then through incredibly complex scientific breakdown of signaling rhythms, they can effectively do what's known as decompose the signal. Now, when I say decompose the signal, what's happening is all of those fibers are contracting at the same time, hence why it looks like a really ugly signal of all the stuff going on. But you could actually parse it into the individual motor units that are contracting at their own frequencies. And so you're going to be able to then define everything that's going on underneath. Don't get me wrong, guys. I do not expect you to fully understand this. This effectively should seem like witchcraft to a lot of you guys. And honestly, that's how it felt to me for the first little bit that I used, because here's the thing. When I talk about how we have a whole lot of motor units, these are the type of outputs they're actually getting. Now, this is actually some of the work that one of my friends did whenever I was at Kansas, helping him out a little bit with the decomposition. I was one of the subjects in the study and was looking at muscle EMG activation. And this is the raw signal, which then notice this is expansion, so that's 100 milliseconds. But then literally you can decompose the signal, and this is looking at 34 different individual motor units. And you can see how there's the different firing frequencies of each of them as we're ramping up force. And this is only to 40% of maximum. So this is only when you're still tapping into, for the most part, a lot more of your type 1 muscle fiber and a lot less of your type 2. And you're going to get even more motor units to effectively go ahead and put in their signal as you go further and further up. Okay, Anyone want to take a shot at saying what I just said, however you were able to understand it? The good news is it gives us participant names in alphabetical order. And so that brings us to Colleen.
I honestly don't know.
Okay. Did anything I just say make any sense?
Sort of.
You can say no. That's all right. Okay. I'm more than happy to go through this and talk it through because you guys are the ones that are actually showing up to lecture. The ones that are going to have to watch the video of this, boy howdy. So just start off at the beginning. Okay. What is EMG trying to do, Colleen?
Like record how your muscles are like contracting and expanding.
Good, good. Okay. Now, when we decompose the signal, what are we then able to go ahead and look at?
Is that where you look at the like expanded view?
Bingo, bingo. So that's when we go from this raw signal to now we've got all of these other individual signals. And what are these individual signals representing?
Different muscles.
Okay, it's the same muscle. It's the same muscle.
Like different parts of it.
Different fibers in the same muscle, exactly. Okay? Now, why is this useful? Because using this type of information, you can then go ahead and look at, do different people have different recruitment strategies? And the reality is, yes, your individuals that are sedentary, they really suck at using their muscles. Individuals that are really aerobically trained, as, oh, Colleen has fled back to muting herself, but that's fair, that's fair. So if we were to put Colleen on one of these, we would see that she does a really good job of tapping into those type 1 fibers and sending more and more signals to them, but she doesn't really tap into her type 2 fibers until she's at really high percentages of her max. And well, even then, she probably taps out with all of her fibers being recruited when she's only about 60 to 70%. When you look at individuals that are very strength power trained, so if we were to take Blaine and hook him up to it, we would see that he's still tapping into new motor units when he gets at 80 and 90% of his max, because now he's literally tapping into those bigger, more powerful fibers. So it's useful because we can look at recruitment strategies, and that's for healthy individuals. One of the guys that I did my PhD with, he has effectively got polio from the vaccine. One of those incredibly rare, fluke things that occur, but it happened. So he had very limited use of his lower body. So when he was put on the machine and compared to normal individuals, I think we figured out he only had 70 motor units to his quad. That's it. Or to his vastus lateralis. Most people have thousands. He had 70. And so his contraction strategy was they were all on board pretty fast, and then they were contracting like mad as they had to work their way up for increasing his maximal volitional contraction. That's what MVC stands for. So it's very useful because you can look at not just healthy populations, but disease populations and how things are going to change over time. Now, so this is giving us other ways that we can look at force production. One of which is we can effectively skip the nervous system by using a stimulator. Now, a stimulator is effectively a two-pronged, metal-pronged piece of equipment that sends a electrical shock to your nerve, which in turn causes your muscle to contract. We piloted this out for my dissertation on myself, and full transparency, it hurt so damn bad that I did not think I was going to be able to get 50 subjects to sign up for this, because it was really uncomfortable. Because A, it's in your femoral, you innervate it by hitting the femoral nerve, which is pretty shallow. So you're effectively right in the inguinal crease. You put the stimulator right there and you crank up the voltage and you give them a shock, and it causes them to contract their quad without any control of it. Now it's useful because we can look at effectively, okay, all right, how much force can somebody produce? Because you find, when I talk about sedentary people being bad at using their muscles, you hook them up to that, you can sometimes see a force production that literally goes up almost doubling what force they were producing. Not because they're being lazy, but because literally they're not able to put the two together and use those muscles as well. Individuals that are really highly trained, they can still see as much of a 10% gain in strength from that stimulator. Now, I was sending enough to completely override the nervous system, which is referred to as a train. So you're actually getting shocked with a number of consecutive shocks in a very short period of time, and at a high enough voltage that you know without a doubt that you got that full contraction. Once again, not a party, did not do that in the dissertation, but it is useful because now we can get an idea for the signaling. Now we can also get the signaling going back to the body, and that's going to be via what's known as both the M wave and the H wave, and that's effectively telling us the signal that we're getting from our afferent receptors inside of that muscle spindle and the Golgi tendon organ that we talked about earlier, and how well they happen to be functioning. Now, what we're going to see is that individuals, once we become more and more well-trained, we actually have an enhanced function of that reflex and of literally the wave being sent to our muscle to get it to contract. Now, this is due to what's known as myelination. Myelination is where we increase literally fatty sheaths around our axons that in turn are going to allow for what's known as saltatory conduction to go a bit faster, which is literally part of why athletes' reflexes and their ability to produce force increases with time and training. This is literally how our nervous system adapts to training, along with increasing connections between neurons and pruning the ones that are no longer useful. So just like our muscles are going to adapt to training, so is our nervous system. Now, we are obviously electrical chemical machines. We send that electrical impulse to the muscle. It then translates into a chemical impulse through the neurotransmitter acetylcholine, which goes back into electrical impulse and then causes a chemical contraction. When we send that electrical impulse to the muscle, there's always a slight delay before we're actually able to produce force. This is what's known as the electrical mechanical delay. And that's literally where the calcium is being released from calsequestrin, all the action potential is going from the neuromuscular junction down the sarcolemma into the T tubules, all the things you're going to have to effectively memorize when you get to exercise phys. Don't worry about it now. It's just important to understand that there's a delay. Now, this is why the Terminator movies are really inaccurate, because if humans ever had to fight a machine, it would be incredibly sad to watch because we are slow. Meaning our best reaction time is going to be about, I believe it's, you can see some folks that are less than 1/10 of a second. Most people are about 200 milliseconds, some even faster than that. Machines can move so much faster than we can. But what's really interesting, when we talk about that force velocity curve, and specifically the high-end velocity, in Muhammad Ali's prime, his jab was literally so fast that by the time your brain would realize he's going to try to punch me in the face and you think I should move, before your muscles would be able to actually contract enough to get you out of the way, you would have already been punched in the face. That's how fast his hands were. So I'm sure you guys have done some of the games where you have your hand on top, and then when you move, your person trying to slap you in the back of the hand. Is like, it's so darn hard to effectively avoid that because, once again, we have these delays built into the system. Any questions about effectively what's the neurophysiology of muscular contraction? Exactly, Evan. So how do we measure strength? Well, we can use torque if we're looking at the individual joints. This could be things like an isokinetic dynamometer. So some of the rehab machines you'd see in the athletic training room. Or we're just going to look at global measures like, yeah, let's have them do a compound movement where we're going to see the maximal force they can produce in the movement, which then is going to result in specific torques at specific joints. Now, remember, guys, when we're looking at that torque we're producing, it's always going to be relative to the angle, and it's always going to be perpendicular to effectively wherever it is attaching to the bone. So we're going to find that the major things that are going to be influencing how strong we're going to be is, well, how much tension we can generate. And that's going to be limited by literally how big the muscle is and how well trained it is. So does it have the ability to produce the energy it needs to in order to contract? Now, after muscular strength, that's just the muscle. We're not looking at the biomechanical effects yet of what's the length of the lever, where does that muscle attach into the joint, and how is that going to influence the ability to produce force. So when we're talking about mechanical advantage, remember folks, we're going to be influenced by what percent or what angle we happen to be working with, where we're also going to see that optimal cross-bridging with our actin and myosin. So some folks naturally have an advantage with their muscles are going to attach closer to their bones, or to their joints. And that's going to allow them to actually contract faster because it turns out it's going to move at a higher rate than if it was at a further point on the bone, but they're going to lose in speed lose in strength what they gain in speed and vice versa. So some folks naturally have these attachments further down, which give them a leverage advantage, which is actually going to allow them to be stronger than what people would predict for their muscular size due to an improvement in that lever arm. So this is just looking at the mechanical advantage you're going to find depending on the angle that we happen to have the muscle at. And it turns out, the biceps is going to be strongest at about 90 degrees, but that's also when your lever arm tends to be the longest away from your body. And yes, it's a little bit weaker when we're above and below, but the lever arm is also shorter for the distance it is away from the center, which is going to give us its own advantages and disadvantages. Now, muscular power is simply going to be that force and then looking at the velocity it's moving. So we're really just looking at the torque of the joint and then how quickly we can get that angular velocity to occur. So if we think back to that force velocity curve, we then overlay it with effectively our own power production. And so if you are to look at power production in any sport, the athlete, if the skill level is the same between the two athletes, the one that produces the greater amount of power is going to win every time. The person that wins the 5K, the 10K, the half marathon, the full marathon is the person that kept the highest power relative to body weight during the race, because that's the individual that was going at a faster speed, and so they're going to finish faster. Just like when it comes to your strength power sports, the athlete that produces a greater amount of power relative to their body weight is going to be the faster athlete, which is probably going to mean they're going to be the better athlete, or at least have an advantage there when skills equal. And then when it comes to things like Olympic lifting or powerlifting, the athlete that can produce the greatest amount of power and power relative to the body weight is going to be the strongest athlete and or the best athlete relative to body mass than everybody else in the field. And so we really care about this power production, and notice the power curve is going to be related to where we see the meshing of the force and velocity curve. So once again, why we come back to the foundations of why we need to train our athletes to develop both maximal force and to develop maximal velocity, so they in turn are going to have not just greater power production, but greater power production throughout the entire range of velocities that athlete's going to attain. So most folks are going to hit their peak power at effectively what's 1/3 of their maximal force production and 1/3 of the maximal velocity they can go in that movement. So if you want to throw a harder punch, what do you need to do? Well, you need to literally have a much stronger bench press, or just pressing in the horizontal plane, because now turns out your maximal strength is going to be higher, and if your velocity stay the same, you now have a greater amount of punching power. The other side is training up that maximal velocity with that hand. And if we do the two at the same time, now we can really produce a lot more power, which turns out is really uncomfortable whenever people are doing that to your face. Now, being able to produce power is great, but we also need to be able to keep that power up. And this is where muscular endurance comes in, where it's how long can we keep up our ability to produce that tension over and over again. And obviously endurance is a pretty big catch-all. We're going to learn in exercise phys, there's a number of different energy systems, and we're going to be preferentially using some of them more than others of them, depending on whatever athletic endeavor we're doing. So it's effectively how fatigue resistant are we? And that's going to be influenced by fiber type, by training history, and by effort that you're putting into that program, and specifically utilizing those muscles and the fibers in those muscles for whatever athletic endeavor you're doing. Now, two more brief things to wrap up on. Whenever we go ahead and do a warm-up, the reason we do this is, aside from helping decrease the viscosity in our joints and allowing our muscles to go ahead and literally produce energy a little bit more efficiently, we're going to actually be able to send nervous signals to the muscles faster when the tissues are warmed up than when they happen to be cold. And the last thing to look at is what's known as a strength curve. So what you're going to find is different activities are going to have an ascending, a descending, or a bell-shaped strength curve. Now, when we're doing something like a barbell back squat, like a deadlift or a bench press, most people are the strongest at the top of the movement. They're the weakest at the bottom. And the reasoning for that is that's when we're in those longer positions with the muscles. That's when we've increased the length of those lever arms, because now the hips are so much further behind the center of mass. The knees are in front of the center of mass, and that's going to create a greater amount of torque that has to be produced. Most people miss those movements in the bottom, not the top. So that's where we're going to see where we have ourselves effectively that descending strength curve, because as we are increasing that joint angle, we're not as strong. Now, some are going to be bell-shaped, where we're going to have the hardest or the greatest amount of force we're going to produce is going to be in the mid-range. For some folks, that can be things like doing an overhead press where they have a really hard time locking out, but they're going to be pretty strong through the mid and then weak in the bottom. And then we can have the opposite, where we're going to have a descending. And that's usually when you're using things like accommodating resistance, like squatting with chains or bands, where now we can actually overload the top of the movement so much that the easiest part is the bottom and the hardest part is the top. And that could be potentially useful because it's training the nervous system to always contract maximally through a full range of motion, which is something we're not going to go obviously further into, but I'm just introducing it because it's something that you should learn about in strength conditioning as a means of why you'd want to use that in a intermediate to advanced training. So, any questions as we've gone through the wonders of muscle and how it all works and comes together? Any questions, Tinks? You want to sing the song of your people again? There you go. There's the song of her people. She decided at approximately god-awful in the morning to caterwaul for a good 5-10 minutes. That was great. 10 out of 10 would not recommend.
Before we close, do you care if I ask you another question about the physics homework?
Yeah, bud. What's going on?
Could you do number 4, please?
Oh, yeah, no worries. Okay. So, when in doubt, guys, set it up. So, we're looking for the force of the bicep. So, initially, we're going to have, this is going to be multiplied by 0.025 meters. Okay. Because that's going to be the attachment. And then on the other side, we're going to have equal to, so the first one we're going to have is going to be, we're holding that weight, so it's going to be 20 kilograms times 9.81, because now we've got ourselves gravity, so I'm just putting G because I'm kind of lazy, which is also going to be multiplied by 0.25 meters. Okay. And then we're going to have also on this side of the center of mass of the arm is going to be 5 kilograms, which is going to be 9.81. Once again, multiplied by G, multiplied by a grand total of 0.125 meters. So once we get through factoring that out, we're in turn going to go ahead and that force that we have, now we're looking at that attachment angle is 86 degrees. So we're going to be taking, because we effectively have the opposite right now, we need to solve for the hypotenuse, which is actually how much the biceps force is producing. So that's going to be the sine of 86 degrees, okay, equals the opposite, which is going to be that force that we have. But what we really want is the hypotenuse, because the hypotenuse is going to be equal to the actual bicep force. Does that make sense, Cam?
Yes, it does.
Awesome.
Thank you.
Do you have any questions?
Nope, that pretty much covered it.
Okay, I just saw you were unmuted, so I wasn't sure if there was any questions there. Anybody else? I'm sorry, I only got through picking on Colleen, Haley, Imani, Jessica, Catherine, Kylie, Sam. Well, Sam, you definitely had some questions, but Sydney, Trendon, and Katie, you guys kind of got away for free, so sorry for not picking on you. I'll try to make up for that next week. That's a lack of enthusiasm I'm getting from that? Okay, that's a lack of enthusiasm for that. That's okay. That's okay. Now, how are you guys doing with your group project? How's that coming along for you guys?
With the way it's kind of going right now, it's just kind of tough to get everybody together because everybody's on a different schedule.
Okay, yeah, I kind of figured everybody's kind of shot the heck. If you guys are having issues with your group, and not like, people are just being jerks, but, like, it's just literally like, this person's got is back home and their internet connection is effectively, somebody holding an antenna in a funny angle and hoping that they can get a little bit of a Wi-Fi signal. We can try to figure something out. So effectively, instead of you guys trying to put together your presentation together, it's just more individualized. Like, just don't worry about that group presentation. Just worry about your own presentation, and just try to do whatever pieces you can that way. Like I said, if your group, you guys all are in a good situation where you got a time, you guys can all, meet online at the same time to go through the stuff, then by all means, just keep going and keep chugging. But if you guys are legit struggling, as a group, don't hesitate to, put me on the group email, and, I can step in and be like, hey, you know what? You guys are doing your best, but obviously you guys didn't sign up to do your class online. There's a lot of confounding variables here. I just want to make sure that you guys do well, and that more importantly, you're learning a better appreciation for changing joint ankles, compensatory patterns, and then changes in recruitment patterns you're going to see in individuals that are elite and then novice. Posted for our group presentation. I believe there already is an example of an older presentation that was pretty good, Kylie, that you guys can go ahead and look at. If it's not up there, I can go ahead and try to get it up there later on. Yeah, I'll double check that later, but I think that should be good to go. So I realized that I forgot to hit record until midway through the lecture, so I'm about to start off effectively from here and run through it again. So if you guys want to be bored and have me run through everything for a second time nice and fast in front of you, then by all means hang out. Otherwise, feel free and head on out for the day, guys. Stay safe out there. Miss seeing you guys in person, and be good. Like I said, if you need anything, just shoot me a message. I'm giving out my cell phone number to you guys if you need it. I'm obviously not going to say it because I'm going to put this thing up on YouTube, and dear God, I can only imagine what happens if the trolls get a hold of that. But, we can talk on the phone if you guys need to, because I really don't like talking to myself in my house. It seems very weird, and I do not like this. But just like you guys, we're all trying to make it work. Okay? So if there's no other questions, like I said, have yourselves a good one, because I'm going right back to talking about how it turns out we have a number of ways we produce force. Specifically, we're going to have an elastic component that's being produced by the sarcolemma, and is also going to be essentially the fascia around the muscle, and then also the tendons and the ligaments. So what we're going to have occur is when we're looking at force production, we've got our contractile component and then the parallel and the series elastic component. So if I'm going to put my hand on the table and then I'm going to go and pull back my finger and let it drop, that right there is showing the effects of the parallel and series elastic component. If I lift my finger up and tap it down, that is an effect of the contractile component. Now, if I pull back and push down, that is an example of using the elastic and contractile component, and that's where you're going to produce the greatest amount of force. And so we're going to find when we're doing a lot of activities, like when we're throwing a baseball, we get the stretch in the shoulder, and that's going to allow us to help produce more force as we're using the contractile elements to get that internal rotation to help us throw a ball a little bit more aggressively. Now, the smallest individual unit for a muscle is what's known as a muscle fiber. These are the individual little cells that are going to have the specialized cellular membrane, known as the sarcolemma, and then the specialized cytosol inside, known as sarcoplasm. Now, what we're going to see is a lot of these fibers are going to run the entire length of the muscle, or at least the point at which they terminate with the pennation. As we're growing up, they're going to grow in length, and then due to training, being physically active, we're going to grow them in diameter. This is going to be specifically what we're looking for when it comes to resistance training, because greater, my gosh, guys, I'm having one of those days. Diameter, which is referred to as cross-sectional area, is going to allow for greater force production. And the basic unit of contraction is the motor unit. Now, the motor unit is literally one neuron coming down that in turn is going to activate a number of individual fibers. And we're going to see that there's a difference between these motor neurons when it comes to slow twitch fibers as opposed to fast twitch fibers. And that are fast twitch fibers, aside from contracting faster, which allows them to also produce a greater amount of power, individual motor neurons are going to be recruiting a higher number of individual fast twitch fibers. Whereas slow twitch motor neurons are going to contract a much smaller number of motor neurons. And the fiber type, which are going to be different based upon where you get a greater amount of speed and power production, you also have a much diminished fatigue capacity because they're going to utilize more anaerobic glycolysis and ATP PCR, so our shorter energy systems, whereas opposed to our type 1 fiber is going to be utilizing aerobic energy systems and specifically be able to utilize fat more as fuel. Now, we also have the way that our fibers are organized. Parallel fibers are going to be longer, which they're running essentially straight lengths the entire muscle, which gives us an advantage for speed, but it takes away from force production. Pennates are going to be in an angle coming in through a midline, which is going to increase force production because we've increased the cross-sectional area, but decrease our potential for velocity. So, for example, with parallel muscles, we've got all of them. So we think about the pecs, we think about the traps, where they're going to be longer fibers, which is going to allow for a greater speed and a bigger range of motion. Whereas when we have our individual fibers that are in that pennate, they're going to have a greater amount of cross-sectional area, so they've got a greater force production, like our deltoid is going to be based upon this, and other muscles like our hamstrings. Now, we're going to find that those fibers are going to recruit in order of slow twitch first, followed by fast twitch, because the body's about efficiency, and utilizing slow twitch fibers is going to be the most efficient form because it uses aerobic metabolism, which is the most efficient energy systems we utilize, and they also produce the lowest amount of force. So we're not using excess force. If every time we contract our muscles, we contract them maximally, you would knock yourself out trying to brush your own teeth or just trying to take a drink out of a cup. Now, as we try to produce a greater and greater amount of speed or velocity, we're going to tap into more and more slow twitch fibers until eventually we start tapping into those fast twitch fibers, once again, based upon what's referred to as Henneman-size principle. We then have our basic muscle actions. We have concentric, where the muscle is shortening, eccentric, where the muscle is lengthening, and isometric, where the muscle is holding the same position and contracting with no change in length. We then have what's known as agonist, and that's the muscle that's causing the contraction, antagonist, the muscle that's working against it. The stabilizer, so this would be the rotator cuff keeping my arm in the position, and the neutralizer, that's stopping any secondary action. Since the bicep attaches up into the shoulder, that can also cause us to go into flexion. The lat is effectively keeping it in a neutral position, or neutralizing that action, so we're only getting that elbow flexion. Now, we then have what's known as active and passive insufficiency. Active insufficiency is when we're not able to produce force because we're in a slack position. So if you think about pulling your wrist over as far as you can, keeping that angle and trying to close your hand completely, you can't really fully make a fist in this position because the muscles literally can only shorten so far. We then are going to see this showing up where you can try this at home with your leg and lifting it as high as you can. We're then going to have passive insufficiency, where if we try to bring our wrist back as far as we can and we close our hand, we can close our hand. But if we're trying to make a fist as hard as we can, we're going to naturally feel our wrist wanting to come to neutral, because that's where we're going to have the greatest amount of force production, and gripping is going to naturally pull that hand into that neutral position. Now, you can see the same thing if you try to lift your leg, your chest, and straighten your leg, where you're going to be limited by that hamstring strength. Now, the next big component to really make sure you understand is the force velocity curve. And this was developed by one of my personal heroes of exercise physiology, Archibald Vivian Hill, in about the 1930s. Now, what you're going to see is that as force increases, velocity decreases, and the antithesis is true. So when velocity increases, force decreases. And so at our highest velocity, we can't really produce a lot of force. Like, it doesn't matter how hard you try to throw a wiffle ball, you're kind of topped out. And then the antithesis is true. Whenever we're lifting a maximal weight, we can't move it very quickly. Think maximal squat, deadlift, or bench press, where the weight's moving glacially slow. And what this informs us on is it gives us information as to why we want to train athletes, and that we want to have them do resistance training to increase maximal force production, and we want them to be doing plyometric or speed training where they're going to increase the maximum velocity. And if you watch and see how I distort this graph by increasing force production, notice we're going to also be increasing the velocity we're going to be able to attain at a number of different points in the continuum. Now, if I go back and then I distort it the other way, we're going to see how now we're going to be able to attain much greater velocities at different percentages of our force production. But if we amplify both of these, that's where we're going to make someone into a better athlete in general, because now they're going to be able to produce not just more force, but more velocity throughout the entire continuum. And that's going to make them a better, more powerful athlete in that sport. Now, we also have the length-tension relationship, which is your muscles produce typically the greatest amount of force at 50% of the resting length. When we happen to be in a shorter position, we're now having a greater amount of cross-bridging, but yes, the cross-bridging now we're starting to get to the end where we literally can't produce any more force because effectively the actin and myosin are just butted all the way up against the end. Now, on the other side, in the fully lengthened position, we can actually produce a bit more force because now we're getting the contributions of the passive components. The problem with it is you can tear them off the bone. That's why it ends abruptly at the end, because literally that's where you would have ripped it off the bone. So yes, you can produce more force when you're getting into the elastic component. However, that's going to be rate limiting in that we can now injure ourselves. So keeping in mind the total tension, yes, you can do that, but that's not something you want to do. Here's a graphical example of that Henneman size principle, where you can see how those bigger fibers are going to show up and how it's going to be related again to the, not just the load in this example. So as we're going up in loads to where now we're doing true maximal temps, where from that first rep, you're pretty much tapping in all of your muscle fibers, but also the velocity. So if we're trying to move maximal velocity, we're going to be tapping in there. And then if you take a set completely to failure, you're going to also be tapping into all of those individual muscle fibers, which once again is going to hopefully give all of them a training effect and allow you to make your athlete or yourself, once again, a bigger or stronger athlete. Thank you guys for listening. I had to double back because I forgot to hit record in the beginning. And if you have questions, comments, concerns, never hesitate to shoot me a message. And stay safe out there, guys. Bye-bye.